Okay, so let's take what we just learned from the previous video about gravitational potential energy and kinetic energy, and let's apply it to some situations. So we're going to apply what we just learned in the previous video. Alright, so here goes. We're going to take, again, these are questions from old IGCSE exams. I don't know if I've mentioned this yet, but this number here, that was the number of question that it was on the test that I took this from. So if that's relevant, that's why it's an odd number. You can see this was question number 11 on its exam. All right, so what do we have here? We have a rubber ball is dropped from a height of 2 meters and it lands on a table. While it's in contact with the table, some of its energy is converted into, and then they say it's internal energy. Internal energy. What's that mean? It means that the inside of the ball absorbs some of the energy. So basically, this is a fancy way of saying heat. Some of the energy turns into heat. All right? That's all. So, anyways. So what happens then? Well, they want to know, in that case, what is the highest possible point that the ball could reach after it bounces? Okay, so we've got the starting point. The ball is released from here, this dotted line, 2 meters, right there. All right, so some of its energy is converted into heat. All right, so you can't get any more energy in than you start with. You start with the potential energy that the ball has right here. Some of that energy is going to become heat. So we'll have less energy than this to convert into kinetic energy. So essentially, the kinetic energy went just before the ball bounces there. Just there is going to be less. Sorry, just after, I guess. The kinetic energy there just after the ball bounces is going to be less than this. And then that kinetic energy will turn back into potential energy as the ball goes back up, but it's not going to be able to reach the same height because it has less energy than it started with. So it's going to reach a smaller height. Obviously this one is bigger, this one's bigger, this one's the same as it started with. So the only answer that we could have is that one, because the ball has to have less energy than it started with. All right, couple more. We'll go through these pretty quick. So we have here a stone is thrown from the edge of a cliff. Its path is shown in the diagram. So this guy throws the rock, boom, like that. That's a stone. All right, so the question, in which position does the stone have the greatest kinetic energy, and in which position does it have the least gravitational energy? All right, so let's start here with, well, there's really only two interesting positions, this one and this one. All right, this one's somewhere in the middle. It's the starting point, but it's not going to be the most of anything. All right, so what is the most of up here? It's the highest position the stone reaches, and that means this is going to be the highest potential energy. The greatest amount of gravitational potential energy will be there. All right, now as you remember, the greatest kinetic energy is just before the stone, just before the stone hits the ground, the object, whatever it is. In this case, it's a stone. So just before the stone hits the ground, that's the greatest kinetic energy. So the problem asks us for the greatest kinetic energy. That's going to be right there, just before it hits the ground. So we're looking for number 3. So we're either C or D at this point. Now the least gravitational potential energy, least, is also, interestingly enough, going to be right there, just at the ground. So that gives us our answer right here. It's actually the same. They're both number 3 for this. All right. Next, we've got a ball is released from rest and rolls down a track from the position shown. What is the furthest position that the ball could reach? Could it get to A? Obviously it could get to A. Then the question is, can it get to B? Can it get to C? Or can it get to D? All right, if it could get to C, then it can also get to D. All right, So we have to decide if the ball can get to C. So let's just do a quick draw over here. If we kind of trace this across. Yeah. Remember, the ball can't get any higher, right? This is the starting from rest, so it has only gravitational potential energy right there. So we cannot get any more gravitational potential energy here than what we started with. If we wanted more than that, we'd have to push it, give it an initial velocity, but we're not pushing it. So the ball cannot get any higher than that line right there. So that pretty much makes it clear C is out of the question, and that means that D is also not possible. The ball should be able to reach point B. So pretty simple answer. That is the furthest that the ball is going to be able to reach. All right, now we have some calculation to do. We're going to calculate with kinetic energy, and then we're going to do a quick calculation also with potential energy. All right, so what we have here is a wind turbine, and we're told the area of the wind turbine doesn't actually matter. They tell us, but it doesn't actually matter for the problem. All right, we're told that the wind is blowing towards the turbine at a speed of 12 meters per second. And they've measured this. 7,500 kilograms of air pass every second through that area right there that we saw previously. So every second, 7,500 kilograms of air pass through that area. All right? So then they ask us, calculate the kinetic energy of the air traveling at 12 meters per second, passing through that area in 1 second. All right? So all we need, it sounds complicated, but it's really actually not that bad. They gave us everything we need. So what's our formula? We have KE is 1/2 mass times velocity squared. All right, so we'll scoot up. Or scoot over rather. I'm going to put mass here, and velocity are givens. Mass is 7,500 kilograms, and the velocity is 12 meters per second. Okay, 7,500, and let's go ahead and write in kg. So there's our mass, there's our velocity. Quite simply, we plug them in and then solve. So I'm going to skip that part and I'm just going to go straight to the solution. Alright, so I'm getting 540,000 joules is actually what the unit is for energy. I believe I forgot to mention that in the energy video. So yeah, joules is our unit of energy. Kilogram meters per second, it's joules. Okay, so let's clean that up a little bit. If we look back at our problem, we can see 12, that's 2 significant figures. 7,500, that's also 2 significant figures. Our answer should also have 2 significant figures, which actually it does, but we want to simplify that a little bit because that's a big number. So we're going to go ahead and 5.4 times 10 raised to the 5th power. All right, because we would go 1, 2, 3, 4, 5. Spots is how many spots the decimal point jumps, so it's 5.4 times 10 to the 5th. All right. Okay, so now we want to do a quick problem with gravitational potential energy, and here's what we have. We've got a farmer is using an electric pump to raise water from a river in order to irrigate his channels and keep his soil moist for his field over here. All right, so he's using this pump, and water comes up, it goes into his irrigation channel. All right, so the water has to rise through a height of 3 meters. Cool. All right, so it tells us how much water the pump raises every minute through that vertical height of 3 meters. And they want us to calculate the increase in gravitational potential energy. Right? So basically, how much does the potential energy increase when that much water goes up? All right, so you might remember the potential energy formula: mass times G times H. All right, so let's get us a little bit more space to work here. I'm going to slide off to the side, and we'll do our working in red. So potential energy is going to equal, oops, we need our numbers. The mass is 12 kilograms, the height is 3 meters. Okay, so mass 12 kilograms times the height 3 meters. All right, and then we have to multiply that by g, which is the acceleration due to gravity, and that's just 10 meters per second squared. We round it off to 10. The more precise number is 9.8, but for the purposes of IGCSE, we can round it off to 10 because 10 is way, way, way easier to work with, so that's what we do. All right, so we put this into our calculator and we discover the potential energy is 360 joules again. So joules is the unit of energy. I'll go ahead and write it out this time. Joules. We abbreviate it with a J. All right. So now we're looking at significant figures here. How many significant figures should we have in our answer? Well, here we only have one significant figure and here we have two. Generally, it's a bad idea to round off to just one significant figure. That it's usually not advised, even though technically we should in this case, because our least precise number is this one. And in fact, that's what you're supposed to do with significant figures when you're working problems like this. You round it off to your least number of significant figures in your initial data, and that will be that one. But the exception to that is kind of when it's just one, and you don't really ever want to round off to just one significant figure. So we're going to round this off to two significant figures, which in fact it already is. So the answer, I'll go ahead and leave it as red, is 360 joules is the amount of potential energy that's added. Cool. Okay, so there's some problems. Hopefully that helps to clarify a little bit of how you work with these types of energy and what you'll have to do for the test and for the class and so on. All right.